28 with you. We'll go to your notes. Let's see, it says use the given 0 to find the remaining zeros of each function. It doesn't say look at the graph. It says use that given 0. Now, Friday we did synthetic division. We're still doing synthetic division today. We're just doing synthetic division with complex numbers. Goal of this section is to find all zeros. So the 0 is 1 plus 3i. That goes outside that little upside down house. And the rest of it's still the same. The second floor of this house is loaded up with coefficients. I'm going to leave a lot of space on here because I'm multiplying by 1 plus 3i. Don't be scared of it. It's just a number. That's the setup. Everybody can do the setup. What do you do with the 1? Drop. Now what do you do with 1 plus 3i and 1? That's 1 plus 3i. Add them. Focus on like terms. Negative 6 plus 3i. Now normally if I had time I'd go off the side and I'd figure out what the product of these two things are. I'm not going to. I have this. And it has an I button, doesn't it? So here we go. 1 plus 3i times negative 6 plus 3i. I button there is the decimal point on your calculator. Second decimal. And that product is negative 15 minus 15i. And after you multiply, what do? You add. So 14 minus 15 is negative 1 minus, negative 1 minus 15i. So I got my 1 plus 3i again. Multiply, and I got 44 minus 18i. And then I add. We got negative 38 and 44, which is what? Negative 8, negative 6, positive 6. 16 minus 18i. And then I add, or multiply again. I got 60, which is exactly what I needed to have because it said it was a 0. So when I do division, I better have a remainder of 0. Now, let's see if you remember anything from Algebra 2. 1 plus 3i is a 0. What's the other 0? 1 minus 3i, conjugate. The other 0 is 1 minus 3i. So I'll just stick a 1 minus 3i out front. Drop the 1, multiply and add. This is going to work out well. You won't even need a calculator for the second one. The i's cancel. Negative 6 and 1 makes negative 5. 1 minus 3i times the negative 5 is negative 5 plus 15i. That seems right. That adds to be negative 6. 1 times 3i is times the negative 6 is negative 6 plus 18i. We get a 0. Now it said, and I'm telling you the hint there is you do this until you reduce it down to a quadratic and then you hit it with quadratic formulary factor. Because this is your remainder, this is your constant, that's your x squared. This is x squared minus 5x minus 6. And you set it equal to 0. And it'll factor. How's it factor? That works. So your other zeros are x equals 6 and x equals negative 1. 1, 2, 3, 4 zeros. What degree was the polynomial? 4th degree. Yep. And there you go. I did the hardest one on your homework for you already. Get that out of the way. This is 5-6. 5-6 is basically just like 5-5, except 5-6 cares about how many flips zeros. Is that at the end of Unit 5, or there's one more section? Either way, there'll be another test coming soon. Stuff that hit the floor.
Yeah, that was there. I still having more nauseous and tired.
12 minutes. All right, so 5-6 is the fundamental theorem of algebra. Fundamental theorem of algebra says that x to the n has at least one zero. At least one. Now, the theorem that's associated with this one says that x to the n has n zeros, real or imaginary. That's the one you use. It's actually called a corollary. This is the one we always refer to. If we see x to the fourth, we expect there to be 4 zeros. If we see x cubed, we expect there to be 3. One, they might be repeated. They might not be real at all. But we expect there to be 3 of them, or 4 of them, depending on the exponent. And everybody should be familiar with that theorem. All right, next theorem in here is the conjugate pairs theorem. And I'm going to put this in nice, easy speak. Weird zeros have conjugates. I don't even know what I have a corollary in here for. Is there anything there? Nothing I care about. Weird zeros have conjugates. And this deals with complex numbers, but it can be anything that looks funny. In this section, they primarily give you complex numbers. Come on. So, an example, we have a 0 at 5 minus 12i. If there's a 0 at 5 minus 12i, that thing looks weird, doesn't it? It's a weird looking 0. What's its conjugate? 5 plus 12i. Now there's another 0 at 5 plus 12i. That's weird. What if we had a 0 at x equals 3? Is there another 0? No, it's normal. There is no other 0 associated with it. Another typical case of your weird looking ones would be something like 12 minus the root of 3. That's kind of weird looking. And when you see those, you think about the quadratic formula. That's where those kind of answers always come from, as far as you're concerned. What's the other 0? Plus. So weird zeros have conjugates. If you see one weird 0, you automatically know there's a second one. And all you do is change the sign in between. So that's the conjugate pair theorem. We've already done some synthetic division, so we kind of got that out of the way. We'll probably use the conjugate pair theorem. Polynomial form, should say form of polynomial degree 5 as coefficients of real numbers. We have the zeros negative 2, negative 3i, and 2 plus 4i. The actual instruction says it's supposed to say form. First off, you find the remaining zeros. There are 2 remaining zeros that you can find real quick. What's the conjugate of a negative 3i? Plus 3i. What's the conjugate of 2 plus 4i? Fifth degree polynomial. How many zeros do you have now? You have 5. You have the 3 given, the 2 that you inferred were there. Now we are supposed to form this thing, so what we'll do is we'll write it in factored form. What factor creates a 0 and negative 2? X plus 2. Now we're going to group these funny looking ones together, like negative 3i needs to be grouped with 3i. What factor creates negative 3i as a 0? X plus 3i. What factor creates positive 3i as a 0? X minus 3i. What factor creates 2 plus 4i? When you enter a set of parentheses, what do you do with signs? Change them. So what factor creates 2 plus 4i? X minus 2 minus 4i. Change signs. Both of them. You throw 1,000 things in a set of parentheses, you change sign 1,000 times. What factor creates 2 minus 4i? Minus 2 plus 4. Change signs. It's always overthink this. If you enter something into a set of parentheses, you change your signs. I actually want us to form it. That's going to make this a little tougher. Form the whole thing. That means standard form. It's not going to be that bad. There's a reason I wanted these things written next to each other. Not x squared plus 3. Present. No, not. What do those pieces do to each other? They cancel. They have a plus 3ix and a minus 3ix. And you'll have x squared minus 9i squared. What is I squared worth? Negative 1. So you actually end up with x squared plus 9. Now this is a little tougher. It is. No doubt about it. It really is. What I've seen teachers do in the past, although students never have much success with it, is I've seen people do this right here. they kind of treat that as one thing. I just saw somebody with the months right there. Do I need to talk about that technique? No? Okay, just so I know. I've seen a lot of teachers try to push that technique. The truth is, kids don't have success with this either way you do it. Personally, I would just invoke the triple distributive property and see what happens. X everything. X squared minus 2x plus 4ix. Then distribute that negative 2. You have a minus 2x plus a 4 minus 8i. And then distribute that negative 4i. You have a minus 4ix plus 8i. You have that minus 16i squared. A lot of stuff cancels out. It always does. You've got a plus 4ix and a minus 4ix. They're gone. You've got a minus 8i and a plus 8i. And they're gone. And you're left with x squared minus 4x. You've got these two pieces here. 4 and a negative 16i squared. What's a negative 16i squared? 16 plus the 4 makes 20. You're still not done. Are you? No. Everything's not in standard form. So what do you want to work with? You want to work with x squared plus 9 times x squared minus 4x plus 20, or do you want to do x plus 2 times x squared plus 9? I don't care. Personally, I do those two. That's well nothing. Let's see, we'd have an x cubed. The inside is plus 2x squared, the outside is plus 9x. And then plus 18. Takes a minute, doesn't it? Is it hard? No. Is it tedious? Yes. That's the difference. A lot of kids want to say this stuff's hard. It's not hard, it's tedious. That's all it is, it's tedious. Are you going to make a whole bunch of mistakes and probably miss every single one of these? Yes. That's a given. Especially when you try to fly through them. All right, what property do you want to use here? Do you want to use the triple distributive property and work from the right to the left, or the quadruple distributive property and work from the left to the right? Triple? Brenton says triple. Brenton wants to work from right to left. So he wants to go this way. He wants x squared everything. You can do that. Doesn't matter which direction you work with. Now you've got 4 terms in one and 3 terms in the other. You're going to write out 12 pieces before you combine like terms. Some kids need that to remember what they've skipped. That's an x to the 5th, plus a 2x to the 4th, plus a 9x cubed, plus 18x squared. There's 4. Ready to go. I feel that yawn deep in my soul. So minus 4x cubed, sorry, to the 4th. Minus 8x cubed, minus 36x squared, minus 72x. And 20 everything, right? Plus 20x cubed, plus 40x squared, plus 180x, plus 360. And we'll stop there for today. It sucks because I wasn't supposed to spend a day on this, but whatever. Welcome back, juniors. Hope you kept up. I just overwrote that, didn't I? What's on out, Allison?